Okay, sorry
Sure.
for that. So I'll be speaking about the manufacturing scale-up of microbatteries in wearable applications. So quite the opposite of what you guys are probably used to. So let me go quickly over what Ensurge does. So we're actually based very close by in San Jose. We have our own facility for roll-to-roll uh, 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 processing, and we're the complete opposite of EVs, are the entire opposite of the spectrum. So we concentrate on end markets in hearables, sensors, in wearables, and sports and fitness wearables. Even something like a phone or a watch would be too big for us. We are concentrating in the half milliampere hour to 20 milliampere hour is our sweet spot. We can go probably up to 100 milliampere hour, but really there's a lot of market in this area which is underserved because people have not been paying attention to very small batteries as things have got as a lot of electronic devices have got smaller. So the key attributes, a small amount of story here. So we actually started in 2020 to apply ourselves into the microbattery space. I personally have a lot of have a background as do most of the team here in the in the on the chip side and the printed and flexible electronic side. We were working on a completely different product for NFC on rolls of stainless steel, making transistors on steel. That market did not go very well, though we had a great technology and scale up. But a market is essential, and so we found that applying the core of our technology, which is making devices on stainless steel, there was a need in the microbattery space, and we decided to learn that from scratch. We after doing a lot of surveys, and doing a bunch of market research and technology application, we found that the pressing need was not for very small batteries, sub one milliampere hour, but really in the 1 to 20, 1 to 30 milliampere hour range, where energy density, safety, and fast charging and surface mount technology would be highly valued. So we decided to combine our backgrounds across the team and hire additional people in the battery space. And around 2020, just at the start of COVID, we decided to enter this field and start to learn how to make batteries on stainless steel. So as I said, we have a pretty extensive state-of-the-art facility here that does roll-to-roll processing, and originally designed for making transistors on flexible substrates, and now it's been applied to microbatteries. So what's the advantage over conventional round cells of of rechargeable lithium ion? So if done right, and if the architecture is done right, what we use is basically a solid state architecture that is stacked. We use ultra thin packaging, edge contacts. We go to a very thin stainless steel substrate. And this is done with a convention. It's all solid state, and we use a conventional Oak Ridge-like stack, where we use a cathode of lithium cobalt oxide and an solid state electrolyte uh, um, of LiPo, and an anode-less architecture, where we specifically do not put down an anode of lithium. So what's the advantages in terms of product and the manufacturing issues? So these are really geared for wearables, where we have to charge very fast, and where we can charge in a manner which is a lot more simple. So these can charge since it's not lithium ion, we can actually we don't have to do a CC CV kind of charging. We can go direct CV. Charging is much faster. We can get to about 80% capacity in well under 20 minutes. This is very valued by a whole host of wearables where user time is not spent having to remove the wearable or something like that for extensive amounts of time. You can uh, uh, take that off and have it placed back quite quickly. Of course, in order to achieve this, one must achieve impedance, very low impedance interfaces between the LiPo-LiPon, between the cathode and the current collectors. And so that takes a lot of manufacturing work to come up with what is a manufacturable use of different interface engineering techniques, as well as very close composition control of the cathodes. So again, once the impedances are done right, the batteries are able to pulse greater than, essentially put out pulses of greater than 5C. This is very critical, as I will show in the next slide, for actual use cases. So I cannot show a video here because of confidentiality reasons with our lead customers. But if you look at an application which is essentially wireless, which all of these devices are, they actually have a pretty high current demand, and they have to work down to a fairly low residual battery capacity while still being able to maintain, very good performance. So in this case, I'm showing you where even down to a battery capacity of about 4 milliampere hour on the cells. It can drive, basically pretty strong pulses of up to 50 milliamps at for intervals about 240 microseconds, but that goes on for about half a minute. This, in terms of a pulse, that's about it's an over 12C rate. So for a wearable application, for example, a hearable or a ring or something like that, the battery capacities are probably between 12 to 20 milliampere hour. And for the communication protocols, even down to a low capacity of about 2 to 4 uh, uh, milliampere hour, it's important to have all the functions going. And so that's among our advantages. So it's really the fast charging and the high currents and the high and the ability to drive high pulse current. So this is something which it can do much better than, for example, lithium polymer battery. And so a smaller battery, a smaller, thinner battery here can really hunch above its volume and go to much higher energy densities, as well as these advantages. And the net result is that an end user can make a device thinner and faster charging. When we started out, we thought that one of the biggest drivers for solid state would be safety. But I think lithium ion, for the most part, is been encased in hard stainless steel, and the fuse is probably is safe enough. So that's not the biggest driver. But we still have to get by some pretty key tests. So here we have an example of a shorting test. The battery does not overheat. Some of the applications we have seen are where the wearable is in very close proximity to the body, either on skin or actually sometimes placed even in a mouth or things like that. And so we want to be sure that there is, if it's accidentally crunched, there can be no possibility of a fire, or if it's intentionally shorted, that that the heat dissipation is not so much that it's going to overheat and cause a burn. A quick word essentially on the cycling. One of the key challenges that we had to face, in terms of manufacturing, is the LiPo-LiPon system has been around for a long time. Most companies and other entities have focused on substrates which are glass or silicon or substrates of that nature. We actually used our long-term expertise on stainless steel to make these batteries directly on stainless steel, which is intrinsically a hermetic seal on one side. We also have to do quite a bit of work on how to package these cells and hermetically seal them, so that we get good uh, capacity retention, because any amount of permeation of air or moisture, and you will start to lose uh, net capacity of the battery. So our whole, our key advantage in terms of manufacturing is ability to manufacture this directly on stainless steel substrates, which are very thin and flexible, completely eliminating the need for a glass substrate or a silicon substrate, and things like that. So let's go into the manufacturing and scale up. As I said, a lot of other competitors and people who have first tried these batteries when it came out of Oak Ridge labs, they made these on silicon wafers or glass substrates, which are pretty thick, have to be thinned down in order to get the volumetric energy densities of the package up. We decided to go straight to very thin stainless steel. So our substrates are basically stainless steel at a thickness of 10 microns. We process this as rolls. So the roll-to-roll production, as opposed to a single unit substrate, a wafer or something like that, is much more advantageous from a manufacturing side, much better economies of scale. The other part is that a lot of companies which have made these kinds of cells have used microelectronics like fabrication technique, where they use masking layers, 4 masks, 6 masks, to make these batteries. We actually have virtually eliminated masks completely. We use a combination of printed electronics and other forms of patterning to basically completely eliminate lithography. So what this does is we can very simply and easily customize the length, width of the unit cells of the battery, and then we use a stacking approach, which we kind of borrowed from the flash memory industry. And so the number of stacks determines, and the length and the width determine the total usable cathode, and hence its energy content. It goes into encapsulation and into metallization, and then this actually becomes surface mount technology compatible. So it can be like, unlike other batteries which have to be manually placed or pouched or tabbed, these can be picked and placed, and placed directly along with other electronic components. And so, when we got into this field, we were, and we still, we basically had a semiconductor class clean room with humidity control, and everybody, made batteries basically in dry rooms, and we could not do that, and we found it too expensive. It was not operator friendly, or manufacturing personnel friendly, and since other people made these kind of batteries with wet lithography and solvents and things like that, there is actually, if we had scaled that up, there would be a tremendous amount of wet waste and solvent waste which would have been generated. So we made the conscious choice to change our manufacturing flows, so that we could actually operate in a just a standard humidity controlled clean room, no dry room. Operators can walk in without having to resort to special suits. We use zero water. We use no liquids in the manufacturing process at all, and so any waste is essentially the scrap or other relatively small amount of waste. So we have no wet discharge, no wet streams, which have to be which end up in expensive ways of having this of having it disposed of. A lot of this was done basically by process integration innovation, by using the materials advantage, interface engineering, and uh, and the right schemes. Um, the other part is again, we again combine semiconductor like processing, use a lot of techniques from our experience there, applying it to batteries. So since we make very small cells, these are like chips, and choosing, being able to get to yield, being able to choose the unit cells which go into the stack is very critical. So, and doing this at scale essentially demands very high speed tests, since we are testing relatively small cells, which then uh, 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 get stacked. So we took heavily from our experience in the manufacture of chips. We convert, we use roll to roll test essentially in parallel, similar to what is done, in fields of MEMS, or being able to test memories, and be able to test in parallel. This then has to be used in terms of full EIS parameter extraction, and being able to bin them into different classes of die based on impedance, etc., etc., and then coming up also with a low cost ability to test the packages at speed. So in the inset, you see, with increasing amount of layers, you can basically increase the battery capacity. You can either discharge curve via a 3.9 volt battery, uh, you know, in parallel, and then with the increasing amount of layers, you basically uh, uh, increase the capacity. The key is to have the right tests so that we can choose the right die and chips which are assured to cycle in the stack. So that is a lot of generation uh, uh, and understanding of data and defectivity. Um, and I'll go quickly through the rest. Essentially, you can see the unit cells based, on n micron steel can be flexed. They're very very thin. How do you the manufacturing challenges are? How do you handle such thin sheets and cells? Get the right web quality, get to the right surface roughness so that impedances and cell quality is maintained, and then take that all the way into stacking and be able to mount that onto PCBs where they can be tested and used uh, at the product level. The last slide I have is the roadmap. So our key advantage is the form factor. Most solid state, most micro batteries are available basically in round form factors. You might get some custom here and there, but they're mostly round. And so that puts limitations on what product designers can do. So we came up with the stack, which is our bread and butter. We have also filed patents and have started working on wound cells, because there are a few applications which actually do like wound or oval cells, and so we're that's something else we're working on. But the biggest advantage is for some applications we've seen, and hopefully they become real, is in getting to very very thin curved or flex applications. These are in pretty advanced wearables, still in the research stage, I'd say, where our total unit cell stack, one layer of the battery, is only about between 25 and 30 microns thick. So by uh, good engineering of the package and applications, we can basically have relatively flexible batteries or curved batteries, which can open up new form factors. And these can be used in products where the battery can be, about where the battery needs to be as thin as 50 or 100 microns. To be sure, these are not applications which are yet mainstream, but they're starting to come through. Uh, and so, in summary, I'd say we are in microbattery space, all solid state. The applications on hearables, fitness wearables, IoT, and medical side. We are transitioning from dev into manufacturing, going through all the pain of yield and rel qual. So we're not yet done, but on the way there, we have made a lot of progress in essentially a short 4 years, and hope to get to being able to get this out of the marketplace where we already started to sample with our lead customers, and then as we keep improving our quality, start to get out in the general marketplace. So that completes my talk. Hopefully, there's some time for questions.